This is exercise 4.7, question 11. We're told that ABCD is a parallelogram, meaning that opposite sides are parallel. So AB is parallel to CD, and we know that AD is parallel to BC. We're also told that the diagonals, which are diagonals AC and BD, that they meet at this point R. And a line PQ, so this line here, PQ, is drawn through R, where P lies on AB and Q lies on DC. Now, the first part of the question is that we have to prove that triangle BPR is congruent to triangle DQR. Now, working with the fact that we have a parallelogram, we can use properties of a parallelogram to prove this. Because we know parallelograms have opposite sides parallel, we should really start looking at, in this case, you would look at alternate angles, because you're not really going to find corresponding or co-interior angles in these two opposite triangles. So we can see that angle PBR is equal to angle RDQ. So we'll just write that up first. So we have angle PBR equals angle RDQ because they're alternate angles, and the lines that are parallel are that AB is parallel to CD. So we'll just mark in those equal angles. Okay, so we're still looking for more information to prove congruence here. If we look at a backward Z here, we've also got that angle PBR equals angle RQD, also by alternate angles, because AB is parallel to DC. So we can write that up as well. So angle BPR equals angle RQD, and they're alternate angles as well. Now you should mark those in on your diagram as well. That way, when you're trying to see which congruency proof that you're using, it'll be, you'll be able to see it visually. Now we can see that we have two angles in those two triangles that are equal to each other. We can also see that these two angles here are vertically opposite angles. However, we can't use this because AAA is not a congruency proof. The only congruency proof involving two angles is AAS. So we need to find an equal side in both of these triangles. Now, if we look at whatever properties of a parallelogram that we know that opposite sides are parallel. We also know that opposite sides are equal. However, that doesn't help us in these triangles, in triangle PBR and triangle DQR. The only other property of a parallelogram that we can use is a property about the diagonals. Now we know that in a parallelogram that the diagonals bisect each other. So therefore we know that BR is equal to RD because the diagonals of this rhombus, which are AC and BD, bisect each other. So we're going to write that up now. So we've got BR equals RD, diagonals AC and BD bisect each other, and I'll just put that information in on the graph as well. So I've just marked that information on the diagram, that BR equals RD, and we've written here that BR equals RD, diagonals AC and BD bisect each other. So now we have enough information to prove that these two triangles are congruent, because we can see that we've got two angles and a side. So therefore triangle BPR is congruent to triangle DQR, and the reason is AAS. And notice in the naming of the two triangles that we've preserved order. So B is the side with the arc, the angle with the arc. P is the angle with the little circle, and then R is the blank angle. And again, we've gone from arc, circle, blank for DQR. Now, in part B of the question, we have to hence show that PB is equal to DQ, And we can see that these are just corresponding or matching sides of the congruent triangles that we've just proved. So we can write that up first. So we've got that PB equals DQ, matching sides of congruent triangles. We can also mark in those lengths on the diagram. So I've marked in those equal sides that PB equals DQ with a double dash. And hence we have to show that AP is equal to QC. Now, because we know that ABCD is a parallelogram, we know that AB is equal to DC. And hence by subtraction, we know that AP is AB minus PB, and that QC will be DC minus QC. So hence we can show that AP equals QC because we're just subtracting two equal side lengths. So we'll write that out. So we're saying that AB equals DC because opposite sides of a parallelogram are equal. Because it is a parallelogram, we can use properties of a parallelogram in our proof. And then we can say, well, AB minus PB is equal to DC minus DQ because we're talking about all equal side lengths. We know that AB equals DC and that PB equals DQ. Therefore, AP minus PB would equal DC minus DQ. And then on the next line, those subtractions, AB minus PB happens to be AP, so we can write that down. And DC minus DQ is actually the length QC. So therefore AP equals QC as we've been required to show. And that's the end of the proof.